And then as you circle those interesting points, I want you to think about why you think they're interesting. That's kind of where we're at there. So just circle why they're interesting. Interesting points on the graph is what we're looking for there. And then we want to figure out why they might be interesting there. So just give some thought to that. There's no right or wrong answer necessarily here. How about that? Kind of taking a chance here to letting y'all could all circle what I don't want you to circle, and I have to chase a rabbit off some other direction today. But I think most of you are going to look at the same type things that I'm looking for there. So, interesting points. How many interesting points did you find, Lauren?
I found 5.
1, 2, 3. Okay. Anybody else find more or less than 5? Oh, I love everybody. Probably did you? 7? Okay. Oh, okay. So Hamilton used test-taking skills. Okay, there's dots on here. Therefore, that must be the interesting point. So let's circle them. Okay. So okay, there's nothing. So maybe that's it. Okay. Who would like to describe some of the points that they circled there? I can't look at the graph, so you got to describe to me what they look like. What makes them interesting? Whoops. What makes them interesting? Come on, somebody tell me why you think they're interesting. Changes in direction, okay. So, what makes a point interesting? Something that makes it interesting is changes in direction. Okay. Anything else that makes a point interesting? When it's not on the line, like these two here. Okay. Not on the line. Good. Okay. Anything else that makes it interesting? Sudden changes in slope. Ooh, that sounds like a calculus word there, doesn't it? Sudden changes in slope. Okay, so where are there, give me the x-coordinate of a point that qualifies as interesting then. -3. 1, 2, -3. Okay, so that's an interesting point. Give me some other interesting points. Terry, you got an interesting point for me? -2. Okay. Anybody got another one for me? Nick, you got any interesting points for me? 1. Okay. Any other interesting points according to these definitions or your own? 5. 5 is interesting. Ooh. Does 5 fit one of these things here? Oh, so why is 5 interesting? It is interesting. It's a dot. Why? It's got a red dot on it. 5 is interesting. Yes, that is. It's almost across from that. Any other interesting points there, people? 7, which would be somewhere over here. 3, right here. Okay. Any others? I see -5. All right. And 6. Okay. I'm going to circle these two in green because they are interesting, and they don't fit any of our interesting reasons over here. I think all of the others fit one of our interesting reasons over here somewhere. Okay? And yes, I will agree with you that these two down here are interesting simply because they're not on the line. Makes you wonder what's going on. Maybe we should put some glasses on them there. Who knows? But you know, they are interesting, but we're not going to focus on those. I want to focus on these other 1, 2, 3, 4, 5, 6 points there. Okay? And I want you to tell me, other than they've got a red dot, other than they're on the graph, tell me something all of those 6 points circled in blue have in common. They're on the line, okay? They're all on the graph. They're all got a dot. But what's something they all mathematically have in common? You mean? They're a turning point. Define what you mean by they're a turning point. Okay. The graph is changing turning points. Okay. And you said another word. What did you say? You did. You said, and I wanted to hear it again. Started with an S? What about the slope? Slope change. Well, yes, the slope is changing. But what do we really mean by that? The slope is changing in a lot of places. The derivative is changing in a lot of places. What's special about it changing at these places? Goes from positive to negative, and if it goes from positive to negative, what has to happen? It's going to be 0, okay? The slope changes. More accurately, the slope equals 0. Yeah, Josh, I'm glad.
At one point, not
that one there? Does the slope change from positive to, does the slope change from positive to negative there? No. Uh-oh. Oh, yeah, it's not differentiable. It is continuous, but it's not differentiable. If it's not differentiable, so let's go to this, okay? Slope equals 0. Yes, I'll buy that the slope is 0 at that point there. I'll buy that the slope is 0 there. I'll even buy that the slope is 0 there. However, here and here and here, the slope is not 0. Because, as Josh just told us, these places, the function is not differentiable. What does that mean? Derivative doesn't exist. So we can say that either the slope is 0 or, let's write it down here, slope equals, come on, work with me here, equals 0, or the slope is undefined. Okay? And all of those blue points fall into that category. The slope is either 0 or the slope is undefined. Okay? Now, I want you to tell me something else. Let's see if we can get there. I think y'all can. Let's see. Can we do this? I'm going to highlight, if I can figure out how to, I'm going to highlight some of these points. I said highlight. Boom, 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 boom. Look at those points. Those are all interesting points. They're all points where the slope is either 0 or undefined. What else can you tell me about each of those? Yes, sir.
It's where the slope is positive and goes to negative.
The slope, yep, the slope goes from positive to negative or negative to positive. Here's what I want you to do. I want you to look at each of these locally. What do I mean by locally? What's around? Look right around it. Describe each of these looking at it just locally.
The local minimum and maximum.
The local, what on earth do you mean by local minimum and maximums?
Well, like the first one, it's the highest it gets for a while. And then the second one's the lowest it gets at all.
Okay. Local, max, or min. That's the lowest or highest it gets, highest for a while. This is the Josh definition. The lowest or highest it gets for a while. What do we mean by a while? In the general region. Can you think of any real life examples of local min specifically that a daily low temperature? A daily low temperature, because if you watch the news this morning, it said the low was 49. Does that mean that was the absolute lowest it was anywhere in the world? It just means in this area, right? What are some others? Something that really catches you at home, maybe more so than that.
I guess you could think about like a hill or like a valley in a certain region.
Okay. So what's the highest mountain? Well, if you're talking about in Georgia, I don't know, it's Brasstown Ball. Yes, Brasstown Ball is the highest mountain in Georgia. But that's not the highest mountain ever. That's Mount McKinley, Mount Everest. No, it's actually one in the ocean that we can't see the top of because we're above it. But anyway, yes, the highest one on land. So local max or min is the highest max or min in an area. One that probably plays into you really quite a lot. Quite a lot. What's that? RenWeb? The grades, your lowest. Gas prices. There's a local min, right? Where's the lowest place to buy gas? Racetrack. Racetrack this morning was $2.94. QT, huh? Kroger was $2.84. It's $2.90 at the QT going towards Watkinsville, where Mars Hill runs into Mars Hill. Yeah, and if you go to Sam's and you've got a credit card and you've got a Sam's card, you get it at, I don't know, $2.80 or something like that. Did you know this? If you go to Walmart and buy a Walmart gift card for $50 and walk out to the gas pump, instead of $2.90 per gallon, you pay $2.80 per gallon. Yeah, read the big sign they've got up there. If you go buy a Walmart gift card in Walmart and then walk outside and buy at their pumps, you save 10 cents a gallon on gas. But anyway, we're really chasing a rabbit here. All of those are really local max or min, okay? Because think about, it's cheaper in South Carolina. Gas is always cheaper in South Carolina. Did you know that? They don't have the taxes that the state of Georgia does. So if you cross the state line, you can probably buy gas for 5 to 10 cents cheaper than what you can buy here. Well, does that really matter to you? No, why not? The waste to go to South Carolina. Now, what if you lived in Augusta, which is 5 miles from South Carolina? Now that's important, It might be important to you, If you're just goofing around and you're trying to make your paycheck last till next week, it might be worth driving 5 miles into South Carolina to buy gas cheaper. But if you're headed this way and in a rush, you might not want to. So what we're talking about is local max or local min. Notice that in every case, a local max or local min, for it to occur, either the slope had to be 0 or undefined. And let me say that again because some of you are wanting to argue with me already. For it to be a local max or min, the slope is 0 or undefined. Okay? What about this point right here? What about this point right here? Is it a local max? Is it a local min? Is the slope undefined? Did I just discredit what I just said? What's happening there? Listen to what I said again. For it to be a local max or min, the slope has to be 0 or undefined. The reverse of that is not true. Just because the slope is 0 doesn't mean it's a local max or min. It means it could be. It could be a local max or min, okay? So what we are doing today is we're defining extreme values, okay? And that's what your next slide is looking at there. Extreme values. And what you're looking at now describes the extreme values in math words, which is what we just talked about. Extreme values. F of C is called a maximum if it's bigger than everything else in the interval. This is, in Josh's terms, a while, okay? If it's larger than everything else around it in a while, it's a minimum. Need to change that. If it's smaller than everything for a while around it, okay? So there has to be extreme values, or we can find extreme values if we can find the highest point or the lowest point. Okay? Now, look at this. Describe to me, or tell me what the significance of the square brackets there for A and B are. It includes A and B. Read this statement to yourself. If F is continuous on a closed interval, A to B, then F has a maximum and a minimum. Does that make sense? If it's, why does it have to be a closed interval? If it were an open interval, does it have to have a max and a min? Look at this. Does that have a maximum? Does that have a minimum? That interval is closed, right? Almost the same line. Does that have a maximum? Why not? Why? What's the maximum? What's the point right up next to it? If this is 2, what's the point right next to 2? I'm going to add another 9 to it. I'm closer to it and it's bigger. Okay, but wherever you stop at, I can get a little bit closer, can I? Yes. As long as because it's an open interval, we never get to 2. This thing never gets to an ending. Therefore, whatever, I don't care what number you say it is, if you start saying 1.9 right now and say it for the rest of your life, right after you die, whoever is still here can say another 9 and they're closer than you are. Okay? Same thing for the min. This is an open interval, so it doesn't have to have one. It does not have to have. Does it say it doesn't? No, it says it does not have to have one. So I want to give you another example. Look at this. Does this smiley face have a minimum? Yes. It's going to have a minimum. Does it have a maximum? That's going to be a min, but there's not going to be a max. So it's possible for a function to have both a min and a max, to have neither, or to have just a minimum. Would you agree? All right. The real question is, how do we find the max and the mins? That's where the calculus comes in. How do we find the max and the min? So let's go back to our graph again, and I think y'all know this already. But what did we determine a while ago was true of all of these max and min? What's true at each of those points for the max and the mins? Because all of those would be a local max or a local min. Okay? So the slope or the derivative equals 0, or the derivative is undefined. Okay, now, if that's all it is, then this point right here is a local min or max too. But y'all said a while ago that one that I just circled in red is not a max or a min. Because at that point that I just put the red square around, the slope is undefined.
It has to go from a positive to a negative slope.
Yes. So you've got to have two things. Either the slope is 0 or the slope is undefined, and f prime changes signs. That's how you find extreme values. Okay? So by doing those two things, you can determine if a function has extreme values or where those extreme values are. So do you see the process that we're going to go through? We're going to find the derivative and set it equal to 0, and then we're going to figure out where it changes signs at, okay? Not a hard process. This is where you're going to learn to repeat something over and over and over, okay? We call these points critical points, okay? Some books call them critical numbers. I'm going to call them critical points. A critical point is a place where the derivative is 0, the derivative is undefined, and undefined, and it changes sign. Excuse me, I'm going to back up. Critical points only meet the first thing. The derivative is 0 or undefined. Extreme values, it has to be a critical point and changes signs. Are we clear on that now? Critical points are where the derivative is 0 or undefined. Extreme values are where it is at where the derivative changes sign at there, okay? Yes, the function is defined. I didn't say that because to me that's kind of obvious. So let's look at what I'm asking you to do here, okay? Find the extreme value. Extrema is another way of saying that, okay? Go ahead and get the giggles out. Of the f on the interval -1 to 2. Okay? What's the first thing we're going to do? Find the derivative. F prime. Yes. We're going to take out an x cubed. So we've taken a derivative. Ooh, what did I do that for? Oh, I'm brain dead. That is the absolute wrong thing to do. Let's try this again. We're going to take the derivative. It becomes 12x cubed minus 12x squared. What do we do now? Find the derivative, set it equal to 0. So I'm going to take out a 12x squared, and I'm going to get x minus 1 equals 0 in there, okay? So when is the derivative equal 0? And the multiplicity of 2 doesn't have to be stated. If you're really smart, you'll find out some interesting things that happen.
That's the minimum, isn't it? Or maximum?
No, not necessarily, yeah. What the multiplicity of 2 tells you, this says it crosses the x-axis here. This says it touches the x-axis. It's going to touch it and go right back up at 0. So, and then it's going to turn over and come back down at 1 or something like that. But anyway, so now find the extreme values of f. So where can extreme values happen? They can happen at 0. They can happen at 1. Is there any other place that the extreme values can happen? Those are our only 2 critical points. Those are our critical points. Now, I want us to go back and look at something. With this green line here, is this a critical point? Is this a critical point? Well, y'all said it was the min and the max of that interval. So we have two other points that we need to be concerned with here. Not only do we need to be concerned with the critical points, what else do we need to be concerned with? The endpoints. X equals -1, X equals 2. Well, how are we going to figure out from that which ones are the extreme values? Which one's the highest? How do you think you're going to figure that out? How can we figure out which one's the highest? Plug it in. What's f of 0? 0. What's f of 1? I don't think so. Oh, good question. What are we plugging into? What are we looking for? The extreme values of f. So we're plugging into the function f, the original function, okay? What happens when I plug 1 into the original function? -1. Okay? What happens when I put -1 into the function, the original function? I get 3 times -1 to the 4th minus 4 times -1 cubed, which becomes 7. And what happens when I put 2 into the function? I get 3 times 2 to the 4th minus 4 times 2 cubed. What's that? 48 less 32, which is 16. Which one is the highest the function ever gets? 16. What's the lowest the function ever gets? -1. Do you understand that suddenly you know a lot about this graph now? Could you sketch what this graph's going to look like?
So the lowest that it's going to get is -1?
Yes, right here. Because if it gets because 16 is the highest it ever gets. At -1, it's 7. At 1, it's let's graph this right quick. Let's sketch the graph of this. We know that when f is 2, is 16. So here's 2. It's up here 16. When f is -1, it's at 7. So -1 is up 7, somewhere right in there. At 1, it's -1 down here. At 0, it's 0 right there. What else do we know? What do we know from the derivative?
It touches the axis at 0.
It touches the axis at 0. So tell me something. What's got to happen? What do you think this function looks like now? It's a quadratic function. How do you know it's a quadratic looking function? Okay. The leading degree is 4. What does that tell you? Does anybody remember? If the leading degree is even, does anybody remember? Both ends are going up or down. Are these going up or down? Up. Why? Positive. So we know then that it's going up over here. We know it's going up over here, right? What else do we know? Well, it's got to come down to here. That's a low point. So what do we know is going to happen there? It's got to come back up. It's got to come back. Is it going to go through like that? There's what our graph looks like. The derivative is 0 when x equals 0, so it can't look like that. So what does it got to look? We know the derivative is 0 right here. So what's it got to do? It's got to turn back over and do something like that. But how do we know it goes on the interval from, well, now, wait a minute. Y'all just said this was the extreme value, and then you told me it was going up over here. Very good. Does everybody understand what I just tried to confuse you with? What did we say right here? That 2 was the highest it ever went. And then Jonas said it was going up on the ends out here. Well, how is this the highest it ever goes and it keeps going up? It's the highest it goes on the interval -1 to 2. It never gets any higher than 16 on this interval here. Okay? Yeah, I can see the fog going over there. Let's get y'all back awake here, okay? Let's try this again. Find the extreme values, okay? What's the first thing you're going to do here? We're going to write out the steps, and I'm going to let you work it. Find the derivative. What's the second thing you're going to do? Set the derivative equals 0. What's the next thing you're going to do? Well, let's do this and solve. Okay, what are you going to find in step 2? What are the points that come? Very good. From here, you're going to find the critical points. Okay? CP, critical points. So after you find the critical points, then what are you going to do? That's right. We're going to evaluate F at critical points and endpoints. Okay? See what you can do. So find the derivative, set it equal to 0, solve for critical points, and then evaluate the function at the critical points and the endpoints. And let's see what you can come up with. See if you can get a nice solution for me there. Yeah, I did take attendance in here. Nick, is your iPad not working? Right? How are we going to solve that thing there? How do we solve 1 minus x to the negative 1/3?
Divide by 2.
Yep, so we'll divide by 2, and we'll just get 1 minus x to the negative 1/3 equals 0. What are you going to do with that negative power there, people? Put it on the bottom. Whoops. So we'll make it 1 minus 1 over x to the 1/3 equals 0. Okay? What are you going to do now?
Move the 1 over there.
Move the 1 over.
Or you just add the 1 over.
Yeah. Let's do that. Let's say we've got 1. Leave the 1 over here on the left. And 1 over x to the 1/3 over here. Okay? What can we do now? Okay, we can put it under a cube root, or we can cross multiply. Some of us are saying, I can just look at that and tell, right? But if we cross multiply, we get x to the 1/3 equals 1. So how do we solve x to the 1/3 equals 1? Cube both sides. Yes, it's going to be equal to 1. But if we cube both sides, then that becomes x equals 1 for our critical point. Agreed? Okay. If you did it different, I don't know. What did you do?
Okay, I didn't like pull out a column.
Okay. So you just work from right here. You should still get to the same thing. Should be fine. Y'all lost a critical point.
So
There's two. There's two critical points. It's a good. The fact that there's 2/3 means there's two. I don't know if that's the case or not. But y'all lost a critical point because I've worked this problem before. No, -1 wouldn't make that work, but you've lost a critical point. Who can see the critical point that they've lost? Evidently no one. Ooh. 2? No, dividing both sides by 2 was okay. Okay. What? Let's go back then. Think back. What are we looking for? If we go back a few slides, we said to find extreme values right here. The derivative of f at c equals 0, or the derivative of at f does not exist. Is there a place that this derivative does not exist? Is there a place where the derivative doesn't exist? And if so, how do I know that? X equals 0? You're saying that kind of hesitantly. Why? Look at your derivative. Your derivative is, our derivative is 2 minus 2x to the negative 1/3. What's another way to write that? 2 minus 2 over x to the 1/3, right? What can x not be? No, 0, right? If x is 0, that's undefined, isn't it? So x equals 1 is a critical point, and x equals 0 is a critical point. That's right. We want to know where the derivative is 0 and where the derivative is undefined. So we found that we've got two places to be concerned about. We've got 0 and we've got 1. So we found our critical points. We probably need to amend our steps up here. F prime equals 0, or F prime is undefined. Now we need to evaluate F at what points? F of 1, F of 0, F of what? -1 and 3. Okay? So we need to look at those. That's right. How do we know to plug them into the original? How do we know we plug them into F and not F prime? We want the extreme value of F. The extreme values of F is what we're looking for. So we're going to plug these back into the original equation, which was 2x minus 2x to the 2/3. So when I plug 1 in, I get 2 minus 2, which is 0. When I plug 0 in, I get 0 minus 0, which is 0. What happens when I plug -1 in? -2 minus 2. What's the 2/3 root of -1? How on earth do I even do that? How do I raise -1 to the 2/3 if I don't have a calculating device? Yes, sir. Say what?
I think the function is 2x minus 3x. What was the cube root of?
Now, here's my function. 2x minus 3x to the 2/3 power. What are you saying there?
You wrote 2, and I thought...
Oh, I see. Yeah. I'm sorry.